I have a couple of examples of conservation of angular momentum. Here we have a figure skater rotating at 5 radians per second with arms extended, has a moment of inertia of 2.25 kilogram meters squared. If the arms are pulled in, so the moment of inertia decreases to 1.8 kilogram meters squared, what is the final angular speed? The ice skater, we know, is originally rotating at 5 radians per second. Ice skater has a moment of inertia, so this is the I value that is given originally. By bringing their arms in, their final moment of inertia has dropped to 1.8. So we're trying to find this final angular speed. Now, because there is nothing external to the system, there's no net torque causing the angular speed to change, we can say that the initial angular momentum of the ice skater needs to equal the final angular momentum of the ice skater. There's no net torque. There's nothing external to the ice skater that is causing them to change their speed. Now, technically, there would be a little bit of torque due to the ice, of course, but that's very minimal. In terms of just pulling their arms in, we see a change in angular speed immediately. And so it is okay to go ahead and use this concept of conservation of angular momentum. The final angular speed the ice skater will rotate at depends upon both that initial angular momentum and then the change in I. So initial I, 2.25 kilogram meters squared. Initial omega, 5 radians per second. By decreasing I, they should spin faster. So these kilogram meter squareds are going to cancel. So this omega final is still going to be in terms of radians per second. So 6.25 radians per second. So we do see that they speed up because they brought their arms in. Now, finding I of a person technically is an experimental thing. You have to experimentally analyze their motion to figure that out. So if you were wondering how to figure out I of a person, that is an experimental thing. There's no table to look up on for a human because there's no set human shape or size and that sort of thing. But anyway, we see as I gets smaller, omega gets bigger.